In this video, we're going to look at a dataset that has a collection of spectra measured from PVP and PS, two polymers that are quite distinct and have very characteristic spectra. And the experiment contains many such examples of these data, and by virtue of the fact that these data are collected as part of a depth profile, these polymers appear in different proportions depending on which part of the profile we look at. So this represents an ideal test ground for peak fitting and other techniques for separating information within XPS spectra. A depth profile is performed by removing part of the surface using the ion beam and then measuring XPS spectra. So the dataset that has been generated by this particular profile includes two narrow-scan spectra corresponding to oxygen and carbon, and then a third that represents the silicon that is at the end of the profile when the polymers have been removed, and we're looking at the substrate, which is a silicon oxide. However, the measurement does not include nitrogen, and the reason the nitrogen spectrum was omitted is that one of the concerns as part of this profile is that X-ray exposure may degrade these polymers. To limit the X-ray degradation, the number of scans was limited to the oxygen and the carbon. There's one other change throughout this measurement, and that is the acquisition time changes, and again this is to limit the X-ray damage. But if we look at this carbon 1s and then we display the acquisition parameters as part of a header, we can see that this first measurement was performed in 1 minute about. However, if we scan through these data, we see that ultimately the acquisition time for this polystyrene measurement is now 30 seconds, and again the idea is to limit the X-ray damage as part of this measurement. Changing the acquisition time between measurements would be a problem if we didn't measure peak area in counts per second EV, and the fact that we use counts per second EV means that you can alter the step size between measurements, and you can also alter the dwell time, and these will be taken out of the quantification calculation by virtue of integrating in terms of energy and in counts per second. This means that a comparison in terms of peak intensity between the carbon and the oxygen will be identical regardless of where we are in this depth profile. The use of counts per second and the use of energy in the integration is critical in this sense. The most basic approach to constructing a depth profile is to analyze these spectra in terms of component spectra that are representative of the two polymers. And this basic approach is available on the PCA property page where we perform a linear analysis. And the idea of this is that we identify spectra that are representative of these two polymers. And I'll do this by creating a display in which I can see the spectra, and then I need to identify, very much by eye in this case, that I believe this to be an example of the polystyrene, and then perhaps this one here is the PVP. So if I select these two and overlay these, you can see that in the active tile I've now got two spectra that look reasonably like the spectra that I would expect to see for these two polymers. I've looked at the Beamson-Briggs polymer database, and I can see that these are very similar to the data envelopes that appear for what they call PNVP and PS. So I'm going to make use of these to analyze this data set of carbon 1s that are evolving between the different layers and the interfaces between the different layers of this depth profile. So if I make a selection of all of these spectra, and in the active tile, which is this one with the highlight, I have the two spectra overlaid that I believe to be the two polymers, then I can perform an analysis into these two polymers by pressing the button that says Generate Spectra in the Linear Analysis section. And as a consequence of pressing the Generate Spectra button, I end up with a new data file that contains a number of columns of carbon 1s data. And if I overlay these on a row by row basis and then step down, I can see that each spectrum within this original list of spectra that were selected has been decomposed in terms of these two spectral forms that are representative of these two different polymers. So this is one way of fitting these data with a pair of curves. The Generate Spectra button has taken these two component spectra and formed a new spectrum, which is this green component. And the green component has been chosen to fit the data envelope in a least squares sense. So mathematically, what has been performed is that these two component spectra are treated as if they're vectors, and these vectors form a plane in an n-dimensional space, and there are a set of vectors that we can construct that lie in this plane that are linear combinations of these two spectra, and the least squares calculation for any spectrum within the depth profile is to choose a vector within this plane that is closest in a least squares sense to this spectrum here, and it represents a projection of the depth profile spectra onto the plane that is formed by the polystyrene and the PVP spectra. A depth profile can be calculated from the linear least squares file, and this is performed by adding regions to each one of these component spectra. So if I use the quantification parameters dialog window and I add a region that corresponds to the polystyrene component, I'll specify the name as C1S PS. The RSF for carbon is unity, so I will propagate the region to each one of these polystyrene components and do the same operation for the PVP. Let's change the name again. PVP. So the names will be used as part of the display of the profile, so I'm going to use the custom report to generate a profile from these two columns of spectra that represent the decomposition of the depth profile carbon 1s spectra into these two components. And if I select the regions option on the custom report, then I end up with name formula table that is just simply the two regions, and then I can press the area report. This gives me a table which I could take through the clipboard, or I could create a depth profile that indicates the types of variations that are possible within this profile dataset. When I referred to the linear least squares approach to generating a depth profile as being basic, it's because the fitting only allows for variation in intensity. It does not allow for shifts, and it does not allow for broadening of peaks. And it is for this reason that we generally use nonlinear least squares to analyze data such as these. And this is because during a depth profile we are etching the surface, so the surface is changing. There's a charge neutralizer state because these are insulating materials. It's possible that at each interface there is some interplay between peak position, full width half maximum and intensity. That means that what we see here is not truly representative of how clean these interfaces actually are. So I will now go through and do the analysis again, where I will introduce more flexibility again into the linear least squares approach, and hopefully produce a much better profile that is more representative of the layers of these different polymers that have been profiled using this argon cluster source. The problem with this basic analysis is that we were projecting onto a plane that was formed by two spectra that were chosen at the start of the depth profile. However, as the profile proceeds, the surface changes, the charge state may change, and so these spectra may evolve in some way. They may shift, they may broaden, they may interact in different ways that we need to account for at the latter phases of this depth profile. So rather than projecting onto a two-dimensional subspace, what I propose to do is to project onto a four-dimensional subspace where I calculate basis spectra from the latter phases of this depth profile and combine a PS type shape and a PVP shape that is representative of the end of the depth profile and also include the two spectra that were representative of the start of the profile. I'm going to make use of features on the spectrum processing dialog window in order to calculate these additional vectors or spectra that I'm going to use as part of a linear least squares. We also need to return to the original data set and then copy some of these data to a new file so we can manipulate them independently of the original data file. So I'm going to move across what I believe to be representative spectra of the various layers of the polymer within this data set. So I'm going to copy to a new experiment frame a set of spectra for which I believe even at the very end we can see some evidence of both forms of the polymer. And I've taken the oxygen through too because I propose to use the oxygen as part of the calculation. The signal to noise at the end of the depth profile is not quite so good as the start, and this is because of the reduced acquisition time. However, since we have a large number of such spectra, and for the most part these spectra are similar, we ought to be able to apply principal component analysis to reduce the influence of noise on these data. The PCA property page allows us to calculate the principal components for this data set of carbon monomer spectra, and we can do this by specifying the number of principal components that we would like to calculate, and then we can indicate that we want to calculate all 30 of these that I've specified, and then I can say generate factors. These are abstract factors. These are the vectors that will replace the spectra that are calculated by the principal component analysis. So when I press the generate factors, the processed data is then displaying the abstract factors that have been calculated out of this entire data set of carbon monomer spectra. We've only calculated 30 such abstract factors. That means that data that are presented as processed data beyond the first 30 VAMAS blocks will contain a partial calculation. So the first 30 VAMAS blocks contain abstract factors that we can then inspect. So the first one looks very much like the combination of polystyrene and PVP. The second one has evidence of peaks that we see in PVP that are not in polystyrene. And as we go down the list of abstract factors, we see the variations start to look more like noise, and if we step down we eventually get to an abstract factor that is clearly noise. We see greater variation here because this is where the polystyrene peak is intense, and by virtue of Poisson statistics we would expect the noise to vary as the square root of the counts per bin, hence we see this shape here. But for the most part this is looking very much like the noise we would expect from an XPS spectrum. The fact that we can identify a point in this list of principal components where we believe the abstract factor looks like noise means that we can neglect all abstract factors of less significance than the one we're looking at. And all the abstract factors that are above this in the list represent information that is significant to the data set and therefore provides us the means of estimating the number of abstract factors and therefore the dimension of the vector space onto which we should project our data if we want to produce noise-reduced spectra. Now this relates to the linear least squares in the sense that we chose arbitrarily two spectra that represented the data set. We chose a polystyrene spectrum and a PVP spectrum, and these represented a two-dimensional vector space onto which we projected all of the spectra within the depth profile. Having calculated these principal components, we now have an understanding of how many of these are now significant to our data set. So we've got 1, 2, 3, 4, 5, 6, 7. So I'm going to include actually this one too. So I'm going to say 8 abstract factors. This means we've got an 8-dimensional subspace onto which we can project all of these carbon monomer spectra. And if we do this, we should maintain the information in the spectra. We should see all the shapes within the spectra, but what we should then lose is all the noise that is now accumulated into these lower abstract factors and the partially calculated vectors. The actual noise reduction step involves using the PCA property page option predict using factors. So we have to specify the number of abstract factors that we would like to use. So I've decided that I'm going to use 8 abstract factors, so I have an 8-dimensional vector space, and then I need to take my data set and return it to its spectral form. So I've reset the processing, and now we see these spectra are ready to be predicted using 8 abstract factors. So when I press this button, I then produce a new form for these carbon spectra where the noise has been reduced. And this will be significant when I calculate the spectra that will be characteristic of the end of the profile sequence. Since I'm going to include the oxygen as part of the calculation of these spectra that I'll use to analyze the depth profile, I need to do the same analysis here using PCA. So I'm going to calculate a set of 30 abstract factors, and let's inspect the oxygen once this has been converted to principal components. So we have a peak that is representative of the greatest variation, and that would be mostly PVP. Then we have an adjustment. This certainly suggests that the oxygen peak has shifted as part of this profile, and then we have something that looks a bit like a derivative, so that is another indication that we've got some shifts going on in these data, and ultimately we get through to noise again. Now the difference between the carbon and the oxygen is that when we have polystyrene, there is no signal for the oxygen, and therefore we need to have some vectors in our calculation of the noise reduced data set that actually represent noise, because that is part of the polystyrene data. So let's reset these. I'm going to use 12 because I'd like to have some representation of noise to compensate for the fact that I have noise as the characteristic of polystyrene. So I'll say predict using 12, and you can see that for the most part the PVP spectra have cleaned up in terms of noise, and we still have something that looks a bit like noise for the polystyrene. So I'm now happy I've got a data set that is noise reduced for both carbon and the oxygen. In the basic profile I use just the carbon. In this case I'm going to use both the oxygen and the carbon as part of the linear least squares. So I need to prepare these data so that I can then perform a linear least squares using vectors that are both oxygen and carbon. So what I've done is overlay in each tile one pair of oxygen and carbon from this depth profile. So I've got a scroll list that contains the entire set of oxygen and carbon, so that there's an option on the test data property page that allows me to merge these data as irregular spectra. So when I press this button, a new file will be created that contains both the oxygen and the carbon as a single VAMAS block. Each of these merged VAMAS blocks have been created from the tiles that were arranged in the scroll list. So we see here the individual pairs of oxygen and carbon have been arranged, and when this button merge irregular was pressed, each of these tiles was used to create the new VAMAS block that now appears in the irregular file. So these are now individual vectors that we can process and try and understand the relationship between oxygen and the carbon at the latter stages of the depth profile. At the start of the depth profile, the separation of these two polymers is much clearer. As we step through, we see the oxygen in particular increases and then disappears again, and this is an indication that we do have separation of these two polymers, at least in the first few cycles of this depth profile. However, over the same interval at the end of the profile, we can see evidence there's oxygen in all of these cycles, which suggests that the polystyrene and the PVP are being measured at the same time over these cycles within the depth profile. So what we need to do is identify a pair of these spectra that would be representative of the interface between these two. So we can see an example where we've got something that has a significant proportion of polystyrene and then another one that has a significant proportion of the PVP. And then we can use the spectrum processing dialog window on the calculated property page to look at different spectra. When I look at these VAMAS blocks, I'm looking for a pair of VAMAS blocks which actually I've previously identified as being these two, that provide a nice example of where we have a spectrum that contains varying proportions of PS and PVP. And these work out quite well. If we look at the normalized version of this, you can see that the peaks do line up reasonably well at the wings. That's quite reassuring. And also if we look at the oxygen, there's a nice alignment of these oxygen peaks. So if we want to do a difference analysis of these data, this will work out reasonably well. So if we go to the calculator property page, we've got these two displayed in the active tile. We'll press the difference button with an increment of 0.1 to provide a fine increment between the change from one spectrum to the other as a set of different spectra. So here we have the different spectra, and the problem now is to scan through these data until we end up with something that looks close to polystyrene and another one that looks close to the PVP. So as I search through this list, I look for evidence of the oxygen peak disappearing, and you can see here that as we go down, the oxygen peak becomes smaller, and then I can scan and end up with an oxygen peak which is really quite small. In fact, it looks very much like noise. And the peak we have here for the carbon 1s is looking very much like the polystyrene. The difference between this polystyrene that we see here and the previous polystyrene that I use in the depth profile is this one is representative of polystyrene at the end of this profile sequence. And the task is then to save this as a VAMAS block that we can use in a least squares calculation, and then find the corresponding PVP spectrum that we can use to represent PVP at the end of the profile. There is an option on the PCA property page that helps to copy a spectrum, and it's this save processed copy. And what it does is it copies the selected VAMAS blocks and it adds an extra character to the element transition string so that it moves the copied VAMAS block to a new column. So when I press the OK button, I end up with a new column that is a single VAMAS block containing this PS approximation. So now I need to search for the next spectrum that I can use in a least squares calculation. So we're down here, and I suspect that the PVP will be somewhere further down in this list. And I'll probably get a better idea if I look at the carbon envelope to work out whether I've got PVP or not. That's not quite what I'd expect, so I'm going to increase this a little bit. I'd expect this peak to be somewhat rounded at the top. It's not quite as rounded as I'd like, but this is potentially an example of PVP towards the end of this profile. So I'll do the same operation, and I'll copy the VAMAS block that's currently selected. So now I've got these two spectra, and one contains a significant oxygen peak and an envelope that is consistent with PVP, and the other one looks more like the polystyrene. So I would like to use these now to do a linear least squares analysis of the depth profile. To make use of these VAMAS blocks that have been calculated for the end of the depth profile, I need to move these to the data file that contained the depth profile. So if I use the copy button on the top toolbar, I can move the two selected VAMAS blocks into the data file so that we can perform a linear least squares analysis of the depth profile, making use of these two VAMAS blocks as part of the calculation. Let's select these and overlay these in the active tile. And then in addition, I want to add the two VAMAS blocks that correspond to the data that I used in the carbon 1s analysis of the profile as a least squares calculation. So I'm adding to the two VAMAS blocks I've calculated for the end of the profile, the two from the beginning of the profile. Let's overlay all of these and let's have a look at what we can see in terms of the differences between the calculated spectra from the end of the profile and the actual spectra at the beginning of the profile. We'll normalize these data so we can have a better look at the differences in shapes. And the obvious thing here is that there's a shift. The PVP that is calculated from the end of the profile compared to the beginning, there's certainly a shift there, and there's also some kind of shift associated with the polystyrene. So these represent an expansion of the dimension in the vector space that was used in the case of the carbon 1s. That there was only a two-dimensional plane that was used to project all the data vectors onto that plane, and now we've got a four-dimensional space onto which these data vectors can now be projected. The four vectors I want to use in the linear least squares calculation are now in the active tile. So to conclude this calculation, I simply need to select the set of data vectors and then press the Generate Spectra button. The result is a new file, and the new file now contains not two columns corresponding to the component vectors, but four. There were four spectra in the active tile, and so we now have four columns corresponding to the least squares calculation, and I can overlay on a row by row basis, turning off the normalization, so that we can see what these data now look like when analyzed in terms of these four vectors instead of two. A feature of using four vectors rather than two is that polystyrene can be represented by more than one polystyrene peak, and similarly there's an example of the PVP that is represented by a combination of these two vectors rather than a single vector. And this is because the one doesn't entirely represent each one of these spectra, and if you include a shifted shape that is equivalent to the one that you're trying to fit, then the result is different from just fitting a single peak, and this makes a difference to the shape of the profile we'll ultimately generate. So as you go through this profile, we can see that at various points in the profile, the shapes from the start and the end are used to reconstruct the data throughout this entire profile. So effectively we're allowing a small shift to occur at different points in this profile by virtue of the fact that we've used four, that is, we've doubled up on the PVP and also the polystyrene peaks. To create a depth profile from this data set, we need to define some regions on these data. So let's organize a region for each of these VAMAS blocks that represent the components. Two of these columns are the PVP, so I need to identify PVP columns. Let's display these two in the active tile. So these represent PVP, and we can create a region, and we'll create the region for the different peaks we see here. And that represents a region on the carbon 1s of PVP. And I'm specifying a name that's important. This name will be used in the custom report to calculate a profile based on PVP, and I wish it to apply to both of these spectra that are in different columns. So before I propagate this, I'm also going to place a region on the oxygen peak. This one I will call O1S PVP, and I need to use the RSF for oxygen 1s, so I'll specify the name O1S, bring in the RSF, and then change the name back to PVP. So now I've got the RSF that has been brought in from the element library for oxygen. For carbon it's 1, these are Schofield cross sections, and I've got a region that is defined on the oxygen and the carbon for one of these VAMAS blocks. So I'll need to propagate the pair of regions that I've just created on one of these VAMAS blocks to all of the VAMAS blocks in these columns here. So I'm going to make a selection of the two columns, and I now need to propagate. I'm going to propagate the regions only to all of these VAMAS blocks that I've got selected that represent PVP. The reason that dialog window came up was because there are two columns and they have different element transition fields. You normally would propagate to the same element transition field. I should have a region on each one of these VAMAS blocks that correspond to oxygen and carbon. So now I need to do the same operation, but this time for the two that correspond to the polystyrene. In this case I just need a single region. Create a region, C1S, and I'm going to call this polystyrene. So I've got a region that's defined on one of these VAMAS blocks. I need to propagate to the other VAMAS blocks that have the polystyrene spectra. So we now have a region, and the name for this region is important just as it was for the PVP. So when I do the calculation of the depth profile using the custom report, the names will be used as part of the calculation of the profile, and if the name is repeated, as in the case of both the polystyrene and the PVP, they are both repeated in two different columns, but because they both have the same name, they'll be automatically summed when I create the profile based on the selection. So I now say area report and a profile, and this time I have a depth profile that is much more representative of the interfaces between the polystyrene and the PVP layers. You can see it's much more uniform. If I introduce a display option of a grid, then it's more obvious that the polystyrene is remaining constant for a greater period of time into this depth profile. And the reason that this is a reasonable outcome for this depth profile is that the sample was rotated during etching in order to reduce the roughness of the crater bottom as part of this depth profile, and hence the interface between these layers is much more precise. And you can see where it ceases to be precise when the oxygen peak starts to lift and you start to see evidence of oxygen in all these layers below here. This is where the roughness is causing the blending of the polystyrene and the PVP polymers, and it's the roughness in the crater bottom that is producing this type of effect.